Good morning, everybody. Nice to see you guys all in Blackboard already. We can start with some green check marks, and then we will get going. And while you guys are checking in, if you encountered any problems with the types of reactions or any of the balancing questions from the Learning Guide Unit 6, you wanted me to go through any of that, let's start with that. Apparently page numbers aren't reliable, so if you can give like section, question, number, and letter, we could work with that. But if there's no questions, we'll just move on to 5.1, acids and bases. But I'm hoping there might be a few questions out there with regards to some of the stuff we went through last day, so we can practice up some more balancing. Perfect. Ava has a couple. Ava, if you have a couple balancing questions, I'm sure they're doozies. You didn't print 5. We're on Unit 5 today. Can fill in the blanks as you go, perhaps. If you want to start with any questions, throw them in. Anything relating to Unit 6. I'm going to just jump over to the Learning Guide and we'll see what comes up. If you can just throw one in, we'll get started and then you can figure out what the other ones might be. That'll work as well. So when I left you guys, yesterday I asked you to go through some of the types and balancing. This is my page. Apparently we don't have page numbers anymore on these things. 6.1 practice, after all of the summary. Very last one, balancing. That does look a bit tricky. You have no E on balancing. V and W, question 2, 6.1. V and W. Oh, that looks like a tricky one because of the polyatomic. Oh, you don't get E. I got you, Taylor. All right, let's do E first, and then we will mosey on over to the last couple. Taylor, was it a type of reaction thing, or was it a balancing type thing? So, okay, so when I look at E, I'm trying to identify the type of reaction taking place, and I notice I have compounds to begin. So remember, we're always kind of looking at either side of the arrow, reactants and products. And on our reactant side, I have a metal and a polyatomic. I have a metal and a non-metal. So there's nothing special about this one. There's no oxygen gas to begin with. There's no acid or base to deal with. So this is just a double replacement. Double replacement type reactions can get tricky. But let's see if we can't just balance this out right now. So I'm going to just T-chart it. I know you guys didn't have this luxury of just cutting one out at a time, but bear with me. All right, so we started with silver. This NO3 is balancing as a group on both sides, so I'm going to leave it together because it appears on my reactants and product side. I can leave it as a group. So Ag, NO3, K, and Cl. If I start with those things, I am going to end with those things. So I can write them down. Now I'm going to count. Silvers, I have 1, NO3 group 1, potassium 1, Cl 1. I think, Taylor, you might have been confused because it turns out it's already balanced. Unless I'm mistaken. I think this might be a case of it was so easy it threw you off for a bit of a loop. So 1 silver on each side, 1 group of NO3 or 1 nitrogen, 3 oxygens on either side, 1 potassium, 1 chlorine. I think we're okay, unless somebody wants to chime in and tell me why that may be wrong. Often you'll see these things just left blank. Sometimes people will put in 1s to indicate that, oh yeah, I've balanced that. It was just 1s. So I think that was it. Just a nice straightforward one to get us warmed up, get us practicing counting and all sorts of other stuff. All right, V and W for question 2, 6.1, and then Abby was the last few. So let's do that. V and W. Let's grab V first here, and then we'll do W next. All right, first thing we need to do is identify the type of reaction that's taking place. And we need to figure out if we're starting with 2 things, ending with 2 things, starting with 1 thing, ending with 2, starting with 2, ending with 1. These all indicate different types of reactions. So I'm going to kind of just get it straight in my head that I have my reactants on one side, my products, and it looks like I'm starting with 2 things, and I'm ending with 1 thing. So that is going to be a synthesis type reaction. So our elements, our compounds are combining together. So calcium hydroxide and CO2, carbon dioxide, combining together to give me calcium HCO3. I think that's like hypochlorite or something like that. And yeah, I could see how this would be a tricky one to balance because it's going to be a bit of a pain to count your oxygens and try to get them strained out. All right, so the elements I'm dealing with are calcium. The OH group doesn't stay OH on both sides, so I'm going to have to break those down. I also have carbon by itself, so I'm going to have to deal with that as well. I mean, there's really no rhyme or reason to how I'm writing these things down. I'll probably go calcium, hydrogen, oxygen, and then carbon last. Calcium, hydrogen, oxygen, and carbon last. And then I can start counting these things to try to get them straightened out. All right, so calcium, I'm starting with 1. Hydrogen, I have 2. Oxygen, I have 4. And carbon, I have 1. Now I'm going to do the same thing on the other side. My product side, I have 1 calcium. I have 2 hydrogens. I have 2 carbons. And I have, oh no, there's carbon down at the bottom. 2 carbons, and I have 6 oxygens. Okay, here we go. You guys are going to really test my skills here first thing in the morning. So, I haven't done this. Thinking on my toes. I see that calciums are balanced, so I'm happy with that. They're going to eventually unbalance. The key to doing this question is that I'm probably going to have to balance the CO2 group last. Just because it has less impact on everything going on here. So calcium's balanced, hydrogen's balanced, oxygen's my first problem. I have 6 on the product side and then only 4 on the reactant side. So just trying to think of a way to do this without upsetting the balance of things, but I can't. All right, I'm gonna just go for it and then I might have to go back and start all over again. So here we go. Calcium's good, hydrogen's good, oxygen's not good, carbon's not good. I'm going to try to balance the carbon first. I know I said I didn't want to do that, but let's go for it. I'll put a 2 here. Changes my carbons to 2 and my oxygens to 2, 4, 5, 6. Is that it right there? Two carbons, 1 calcium, 1 calcium. 2 groups of 2 is 4, 5, 6. I think that might be it. Unless somebody can point out my mistake, I think everything's balanced there. I could see how you would try to balance something like maybe the oxygens first. You did that and got it wrong. Well, let's count. Have I made a mistake on counting somewhere here that we're not seeing? I have 2 carbons here. I have 2 carbons here. So carbon's good. I have 2 calcium, or 1 calcium, 1 calcium, 2 oxygens, another 4, 6 oxygens, and 2 times 3. Can somebody tell me what the answer is? Because I guess I could just scroll down on this page. You guys probably have it quicker than I can find it. What did we do here? We did V, J, K, L, M, N, O, P, Q, R, S, T, U, V. So it has it as 1, 1, 1. Yeah, that's definitely incorrect. So what did we decide here? It was going to be 1, 2, 1. There you go. Well, then maybe this is why you guys are having troubles with the last few, because the answers possibly are wrong. So for sure that one should be 1, 2, 1. Maybe this is one of these fancy things that teachers do to see if you guys are just copying the answers out of the back of the book, if you're actually doing the problems. I don't know. Maybe that's me just looking into it too deeply. All right. Yeah, definitely. Let's do the next couple and we'll see if those are wrong as well. Did anybody else have the same sort of issues there, finding the wrong answers? Or getting the answers wrong? So we did this guy, we did V and WX. I can see X is going to be a tough one because that's a combustion. Let's do Y. Did it W, and then that's it for you. Okay, we'll do W for you for sure. Grab it here. All right. Somebody identify the type of reaction first, and then I will see if I can balance it for us. Just throw it into chat while I'm going through this. Y was near impossible. We have PB. The NO3 group changes to NO, so I'm going to have to do those separately. NO. And if I start with PB, NO, have to end with them. Perfect. So you guys are right. It's definitely a decomposition reaction. We have I'm just going to see if I can send this to the back. It'll stop jumping in front of everything. Perfect. Definitely decomposition. We have one thing breaking down into several things. It doesn't necessarily just have to break down into 2. In this case, obviously 3 things. So let's count them up and then we'll see if we can balance. So 1 and 1. I have 2 nitrogens to start. I have 6 oxygens. I have 1 nitrogen over here and 5 oxygens. This is one of these times where you end up with this odd number of oxygens on your product side, and you want to kind of deal with that Because if you don't, then you're never going to be able to balance it because you're always going to end up with an even odd scenario. So because I have this 2 back here, there's really nothing I can do to make this odd on the reactance side for the oxygens. So the first thing I see is my nitrogens need to be balanced. 4, 5, 6, 7. Yeah, what I'm going to do right off the bat, this may seem kind of really strange, but I'm going to put a 2 here to make this oxygen into an even oxygen. And it kind of seems like it's unbalancing everything, but it will likely work out in the end in our favor. So that changes that to 2. That's not what I wanted. The oxygen goes from 5 to 2, 4, 6. So that kind of looks like it ruined everything, but let's see if we can't just sort it out now. So now my lead is unbalanced, so I'm going to have to put a 2 here, which changes this to 2, this to 4, and this to 12. And then my nitrogens are unbalanced, so I'm going to put a 4 here. So that's 4 and 8, 9, 10, 11, 12. Two, 4, 8, 10, 11, 12. 2, 4. I'm thinking that's good. Somebody want to tell me if that's the same answer that's in the back? The back's going to say 2, 2, 4, 1. Hopefully. The answer said something else. Oh, whoever made the answer key to this learning guide was not having their best day, apparently. It says 2, 2, 2, 3. 2, 2, 2, 3. Okay, so the answer in the back says 2, 2, 2, 3. Is there going to be a problem with that? 2 times 2 is 4. Yeah, our nitrogens won't balance if you have 2, 2, 2, 3, because you'd have 4 nitrogens here, and you'd only end up with 2 nitrogens here. So that can't work. So there you go. Did we run into problems with the remaining ones? You probably got them all right, Abby, but you just didn't have enough sort of confidence. You always expect the book to be right or the end of the learning guide to be correct, right? Do I need to do the last ones as well? Are they wrong as well? In terms of the learning guide? Answers. Was there a consensus among getting the last couple wrong? W and Abby, you had another question from above that I didn't get to yet. Y. Letter Y, last one. I'll do Y, and then we'll maybe move on if nobody has any other questions. So there's letter Y. I'm not sure if the answer in the back's right or wrong. Hopefully I can balance it and we can figure that out here. So 4 OH. Looks like we lost Blackboard. Well, we don't have Blackboard for a second. Hopefully the live stream's still working, and if it's not, then I guess there's no way for you guys to tell me that. Maybe if somebody sends me a message in Moodle just to let me know that everything's kind of working in terms of the audio, that'd be really great. Assuming Blackboard stays offline, I'm just going to pretend like you're all there, and then I'm just going to balance this. And then I'll see if somebody could send me a message in Moodle just saying, hey, Mr. Borden, yeah, we can see and hear you. That would be good. So I could be just talking to myself right now, and you could figure it out on the live stream later, I guess, the recording. SO4. Let's try to balance that SO4 as a group. Beryllium, O, H, SO4, beryllium, oxygen. 3, 4, 5. SO4 groups, there's 1. Beryllium, there's 1. I can't do it that way. I have to do it individually. It's just going to be a little extra counting. All right, hydrogen, oxygen, sulfur, beryllium. Four, 6 of those. Sulfur is 1 and beryllium's 1. Hydrogen's 2. Oxygen's 8. Sulfur is 2. And beryllium is 3. I'm gonna check, see if anybody sent me any messages. Doesn't look like it. Just kind of slowly refreshing here. Jump back here. All right, where to start? I don't think it really matters where we start. This is looking like a pretty messy one. Oxygen's kind of working out. That should be 9. I'm gonna make these oxygens even right off the bat. So I'm gonna put a 2 here. That changes that to 8, and now I have 10 oxygens. So that'll do. Hydrogens aren't balanced. I have 5. Maybe put a 2 here. Changes that to 6, 8. Sulfur gets changed to 2. Oxygens 8 and 10. All right, now I'm gonna have to go back and change my hydrogens. My oxygens seem to be good now, so I'm gonna have to deal with this beryllium as well. I could see how you would have issues with this. There you go. Beryllium. Let's put a 3 there. 3 berylliums. 6 oxygens plus another 4 is 8 is 12. Oh, that's 14. And then hydrogens, 3 times 2 is 6, plus another 6 is 12. Let's see what we can do now. All right, hydrogens, let's go back and deal with those. Hydrogens 4, I need 12, so I'm gonna put a 6 here. 6 hydrogens, that also gives me 6 oxygens plus another 8 oxygens. It's 14. Solvers 2, I think that might be it. This is, it's so lonely in here without chat. Seems kind of silly, but... All right, let's see if anybody's replied to me here in Moodle, letting me know that you can still see and hear me. It's negative. All right. Mr. Ross has suggested we put up a timer, and maybe we'll just do that so we don't have to cut anything out later. It's possible that this isn't getting broadcasted at all. So if somebody maybe put up like 5 minutes, and if somebody can send me a message in Moodle, just saying, hey, Mr. Borden, we can see and hear you. If you can, I'll continue, but if nobody sends me a message, then I'll just kind of keep trying and waiting and see what we can do. So we'll put up that timer now and see if we can fix whatever's wrong. Thanks. All right, sorry about that, guys. Well, I don't know why I'm apologizing. The network has been kind of kicking in and out for the last while, so it froze for some of us. Okay, perfect. The network is up and down, and it's been a bit of a mess. So I saw a blackboard cut out, but I couldn't tell if you guys could see me on the live stream. But it seems like some of you continued to see me and some of you did not, so that's kind of a bit strange, but there we go. Can we balance a few more? Even BCBL website wasn't working for a while. Yeah, that's all, I guess, run through the district. So it's just a matter of what's getting sent out of our building here. And it all goes through a TELUS network that's controlled by the province. And I guess if it's not working, it's not working. So we got to come up with a better way for you guys to let me know that the live stream's working. We'll figure something out, or we'll just hope it gets fixed. But we'll just go. You hate TELUS? They're not that bad, Alex. I mean, let's give them a chance. All right, Taylor, you want some more balancing? I think we run into, I will do a couple more for sure, Taylor. We run into these problems with balancing, like the last one I just did. It was like a super, super hard one. And I guess when you're going through balancing questions, you should know that they're not all going to be super, super hard ones. There are going to be really straightforward ones, which is a couple twos, or it might be already balanced. So don't kind of freak out when you see a balancing question, because they, generally speaking, aren't going to pick super difficult ones for you guys to balance. And it's just kind of one of these things where you see all the hard ones and you think, oh no, I'm not very good at this. Well, some of them are going to be hard and some of them are going to be straightforward, and you just kind of hope that you got an easy one. So Abby, you wanted me to do this one again? Oh, that was a lot of work, sitting here talking to myself. I guess Mr. Ross was listening to me, so that wasn't complete isolation. First of all, I have it up here as 2361. Did anybody else get that? And is that what the answer in the back said as well? Question X between W and Y. Is there no letters in there? This learning guide stuff's just kind of falling apart. Of course, this is our first time through it, so these answers that are coming up as wrong, sometimes it's just one of those things where we run into these problems and kind of go with it. Yes, it says 2361. All right, so maybe I can just explain quickly how I did it, and then maybe you can just kind of pick up from there. So this is maybe just to explain my thinking on Y here. And this is looking like a double replacement. No, this is a neutralization reaction. And the reason it's a neutralization reaction because I start with an H and I end with an OH, and then I have water. So H gives us our acid, OH is our base, and then we have some water being produced there. All right, a couple things that I needed to get out of the way. The beryllium down at the bottom here, it only shows up in one spot, so I had to balance that one. So maybe that one I probably should have done first. So once I got beryllium balanced, that kind of changed my oxygens and hydrogens up here, and then I could deal with it from there. So you always want to try to do the things that show up only in one spot first, because it doesn't really allow you any opportunities to kind of balance things out if there is just that one spot where it is. It's not just going to kind of magically work. So the beryllium, because it was just by itself here and just by itself here, that needed to get done first. That changed my oxygens and hydrogens, and it also made my oxygens even on both sides, and my hydrogens. So I think once you balance the beryllium, it should kind of fall into place. The next thing is the sulfurs I would do next. So I would go, hydrogen isn't balanced, 6, and 6 is 12, 6 is 12. I have 2 groups of 3 here, and I have 3 groups of 2 here. So there's 6 and 6, and 6 times 2 is 12. So I'm thinking the hydrogens is balanced, unless I'm missing something. Oh, I see what you guys are saying. You're saying I just didn't put down the number 12. You have a 4 there, not a 12. No worries. You don't have to apologize for me doing questions. That's what we're here to do, right? We're here to kind of learn and get the difficult ones out of the way. So that one's that. Maybe I'll do X, because I think somebody was asking about X, or they're saying there was no X. I have an X here, this combustion one. And I think Abby, you're saying that also question X between W and Y. Let's do X, it's a combustion, and then we'll move on. So I did want to get to some new material today. All right, X. So immediately I see my products are CO2 and H2O, and the only time we end up with products that are CO2 and H2O is if we have a combustion reaction. So this is pretty easy to identify. And I also see that I have oxygen as a reactant. So it's important to be able to identify that. And I've mentioned this before, combustion reactions are always going to be the most difficult to balance. It's because of the problems you run into with the oxygens being in 2 spots over here. You're always going to end up with 2 here, and you're always going to end up with 1 here. So you're going to end up with these 3 oxygens on the product side. And when you have these 3 oxygens, everything kind of is messy because of that. So CHO, I have 8 carbons, I have 18 hydrogens, I have 2 oxygens. CHO, it's always going to be 1, 2, 3. All right, I'm just going to go through it and balance the carbons and pretend like I don't know any different, and then we'll see where we end up. So I'm going to put an 8 here. Gives me 8, gives me 16 and another 17 oxygens. That's where we run into these problems with this odd number of oxygens here. And you'll see that there's an easy way to deal with it. Some people will balance by putting like a half numbers in here. So let's balance our hydrogens next, and then we'll see where we end up. Hydrogens, I have 18, so I can put a 9 in here. That's going to give me 18. Oxygens, I have 2 groups of 8 is 16, and I have another 9. So that gives me 16 and 9 is 25. And there's no number I can put here to give me 25 oxygens. 25 times 2 is 50. It just simply won't work at this rate. So what I need to do is just double everything. So combustion reactions will almost always work out this way. And why I double everything is to get an even number of oxygens on this water molecule. And that's just going to be the trick that makes everything kind of work. So here we go. I'm going to put a 2 here. I'm going to change this to a 16. I'm going to change this to an 18. I might need to break out my calculator here to count these oxygens. 2 groups of 8 gives me 16. 16 I have there. Let's just look at my hydrogens. I have 36. And over here, 18 times 2 is 36. So that's happy. Now I need to count my oxygens on my product side. You added incorrectly. Okay, that's minor. 16 times 2 is going to be 32. And then I have another 18. So 32 and 18 is 50. So this goes to 50 oxygens. So I can put a 25 in there. So those numbers just got really, really big because I doubled everything. And there's another method where people will put in front of the oxygens here, they'll put in something like 12.5. And you know you can't have half a molecule. But then once you have something like 1, 12.5, 8, and 9, you just double everything to 2, 25, 16, and 18. And that's another method for balancing combustion reactions. You'll see if you were to look online or something like that, you'd see those. So there you go. Combustion are the most difficult in my opinion, but they always work out the same way. You kind of, you go through it and you realize you have this odd even thing happening with your oxygens on the right. So if you just double everything, it'll work out for you. And if you go through it, again, I've obviously done these a lot. If you go through it again and again and again, you see the pattern develop. And when you see a combustion reaction, if it just doesn't balance right off the bat, like some of the smaller ones like CH4 and O2 produces CO2 and H2O. The really small hydrocarbon ones, those ones will balance right away for you. But as soon as you get into like C6 and above, once you get more carbons, then it all of a sudden you have to double everything. So there you go. I did want to talk about some acids and bases here, and we do have about 40 minutes, so I guess just have a break somewhere in here. I'm going to just jump in the acids and bases stuff and then maybe take a break, and we won't do 2 sections today, just the 1. So this is unit 5.1, and unit 5 is super short. It has acids, bases, and salts, and that's it. The chemistry unit so far has been a lot of kind of process-oriented stuff, forming the compounds, balancing, kind of more like math. But now we get into this acids and bases section, and it kind of goes back into a little bit of memorization type things. So there's some specific things you need to kind of understand and specific reactions that you need to be able to recognize. So that being said, we'll just jump into it. Now, of course, we talked about acids and bases a little bit when we started dealing with neutralization reactions, because we needed to be able to identify what an acid was and what a base was. So in order to be able to identify those things, we had to kind of do this stuff already. So acids and bases are really common. You have tons of acids and bases in your house. You have acids and bases in your body, keeping everything working properly. And we just basically look at their chemical structure in order to figure out if it's an acid or a base. So acids and bases can be dangerous. You can get really strong acids and really strong bases. And it suggests that you never try to identify if it's an acid or base by taste or touch, which is kind of funny because in the chart, we can identify acids by taste or touch. So we don't recommend you try chemicals to like taste them, but in general, acids will be very sour, and we'll run into a bunch of other sort of things that happen with acids and bases. So we have a pH scale. It goes from 0 to 14, and right in the middle is 7, and 7 is neutral. So if something has a pH of 7, it's neutral. If something has a pH of 0, 1, 2, 3, 4, 5, 6, we call it an acid. And if something has a pH of 8 through 14, we call it a base. So this tells us how strong an acid is or how strong a base is. And yeah, Ava, we're only doing the 1 section today. I I think we'll just do this one. So the strength of acids and bases measured on the pH scale, it's a logarithmic scale. So just like the Richter scale we talked about, when we had an earthquake on the Richter scale, we said, oh, it was a 7 on the Richter scale and something was an 8 on the Richter scale. That was an increase of 10 times. And if you had a jump of 2 on the Richter scale, so you went from 5 to 7, that's 10 times 10, that's 100 times stronger. And that goes the same for acids. If you have something that had a pH of 0 and you compared it to something that had a pH of 2, because you're going 2 steps, each step is times 10, so times 10 and 10. So something that had a pH of 0 is going to be 100 times more acidic than something that has a pH of 2. It's kind of weird how it goes from 0 and down. So same as the Richter scale, you guys had a really, did a good job of that in the learning guide for the Richter scale. Most of the questions there you guys did just fine. So we can measure the level of acidity with something called a pH indicator. And I wouldn't be surprised if many of you have encountered these before. And the most common is litmus. And then you can have a universal indicator, which is the one you probably have seen before if you have a pool or a hot tub, or even if you've maybe tested soil in your garden before. And then you have other ones like bromothymol blue, phenolphthalein, and there are natural indicators like cabbage. So I was just talking to Mr. Beetlestone, and he was saying that, because I was digging through to get some chemicals and indicators, and he said, oh yeah, we do acids and bases in grade 7. So if you were with Mr. Beetlestone in grade 7, you've seen many of these things before. It's kind of funny how science works that way. You do like ecosystems in grade 6, I think, and then you see it again in grade 10, and then you'll see it again in grade 11 or 12, biology. Just kind of same stuff gets recycled again and again. We just add a little bit more complexity to it. So in your data book, you guys have a chart that indicates the pH scale, and it shows where some common items kind of fall on that scale. And it has all of the indicator colors that are on that scale. So this is right out of your data booklet. This is page 3. Of course, it's in color. If you printed off your own data booklet at home, it's not going to be in color, but the shading will be different. So here you can see the pH scale. The really great part about most of the acids and bases stuff is that you don't have to memorize a lot of stuff. There are a few things that come up, but if you can just look at your data booklet, you have all of these things on here. So you have the scale from 0 to 14. It says everything over here is acidic, everything in the middle at 7 is neutral, and everything over here is basic. So you have something like stomach acid, which is hydrochloric acid, which has a pH of 1, and then 10 times less strong, less pH is lemon juice, and then grape juice, tomatoes, bananas. Milk is slightly acidic at a 6, and then in the middle we just have water, which is completely neutral. And then basic, you have something like eggs, baking soda, soap, ammonia, bleach, oven cleaner. And there you go. So if we were to compare something on the pH scale, let's say bananas and a lemon. You've eaten a banana you've likely eaten a banana before. It doesn't taste very sour. It's not highly acidic, but something like a lemon is very acidic. So if I go 1, 2, 3 steps, that means the lemon is 10 times 10 times 10. So 1,000 times more acidic than a banana. And then milk compared to lemon is 10,000 times more acidic, going from milk to a lemon. So you guys have encountered many of these acids because most of them are foods. When we start talking about bases, we start talking about cleaners. So things like baking soda, soap, ammonia, bleach, oven cleaner. These are all kind of common bases you'll have in your house. There will be a ton of questions, not a ton, but there'll be some questions that ask you to kind of use the indicators. They'll say, if I put something with a pH of 8 and I put it in some methyl red in it, what color would it be? So you'd have to go down and say, oh, that's yellow. And you'd end up with stuff like that. So I'm going to just slide over here. And I have some indicators next to me here, and we're going to maybe look at a couple of them and see how they react. So I'm going to leave up this chart, and we'll kind of refer back to that. But the first thing I'm going to look at is litmus. So litmus is red or blue. And if litmus is put in an acid, it turns red, and if it's put in a base, it turns blue. But you're thinking, well, Mr. Borden, isn't there two types of litmus paper? And you're right. So over here we have blue litmus and red litmus. And does it matter really? So this is kind of a question. If we have something like red litmus paper, which just looks like it's actually kind of this pinkish color, it's red to begin with. So if I put it in an acid, it shouldn't change color. But if I put it in a base, something that's basic, you can see how it kind of goes from that red color to kind of a bluish color. So that's red litmus turning blue. And then if I had something like blue litmus, and I put it in the same thing, notice how it doesn't change color. It just stays blue, but it gets darker because it's wet now. So if I took blue litmus and I put it in an acid, here's my little acid, you can see how the blue litmus now changes to that nice red color. So the idea here is it doesn't really matter what litmus paper you're using. If you put blue litmus in a base, it'll just get wet. If you put blue litmus in an acid, it'll change to red. So you can run into a problem where you have something that's neutral. It's not an acid or a base, and you put the litmus paper into it, and it doesn't change color. So if it doesn't change in an acid and it doesn't change in a base, then what you're testing is likely neutral. Now, probably some of you have a hot tub or a swimming pool at home. Does anybody have a hot tub or a swimming pool at home? You've probably tested the pH of the water before to determine the exact pH of the water, because you want to keep the water in a good pH range. Perfect. So this stuff here, it's called a universal indicator, and you pull it out and it has this nice kind of orangey color. And if I put it in something like an acid, you can see the acids are all kind of these red colors. So I'm going to put it, maybe I'll tear it into two here so we can test it on our acid and our base. If I put it in an acid, it immediately kind of goes to this kind of reddish color. So I give it a second, and then if I want to know what pH it is, what I do is I just compare it to the scale here. And I see it's looking like about a 2 on that pH scale. So, no, that's not perfectly clear for you guys. Give you an idea. Let's use the other half and test our base here to see what color that changes to. So the base, I need to mix it a bit. It's not super strong. It's kind of going a bit of a greeny color. So if I were to compare it here, it's looking almost neutral, if not an 8. So very weak base I've mixed for our demonstrations today. So that's a universal indicator. Have you guys used those before on your pool? Something similar to it? Or your hot tub? Probably have, if you have a pool or a hot tub. There you go. We have other things that are called indicators as well. So I have a couple here. I have this guy, which we're going to look at. It's bromothymol blue. And then this one is called phenolphthalein. You guys probably can't see it, but we're going to use these two here in a second. So I'm going to just switch back over to the chart, and we're going to see what should happen with bromethymol blue and phenolphthalein. In my class, if I teach science in a building, I make my students say phenolphthalein with me, because when you see it written, there's like a PH, ENO, PH, HALEIN. It's kind of a really weird word. And when students first say it, they never say it right. So for all I know, I could be saying it wrong, but phenolphthalein is what it's called. And you can see behind me here, phenolphthalein it'll be completely colorless in anything that's kind of acidic. And then once you start getting up to about a 9 or so on the pH scale, it starts to turn in this pink color. You said it, thank you, Taylor. So we're gonna see if we can't find something that's maybe a bit strong. I'll mix up my base a little bit more. See if we can make it turn pink. Now I know Ava loved the color of, what was it, copper 2 chloride, said it was one of your favorite colors, that like really cool blue color. I think the phenolphthalein pink is a pretty cool pink. So that's the first one we're gonna look at, it's phenolphthalein. And then the next one we're gonna look at is bromethymol blue, or bromethymol. I think it's spelt 2 different ways. So this one says bromethymol blue, and then the one that I have written there is bromothymol blue. It's the same stuff. So bromethymol blue is going to be a yellow color in an acid, and then if we put it in a base, it should turn this nice blue color. And it starts off life kind of like a brown color. So there you go. I'm gonna jump back over here. Let's maybe do our bromethymol blue first. I'm gonna grab 2 just empty beakers. All right, so I'm gonna put a bit of an acid into this guy, and then see if I can't get a bit of a base going in this one. Mix this up a bit. All right, so you can see it's a clear liquid here, and bromethymol blue starts as this kind of brown color, and according to my my chart here, that this bromethymol blue should go, and it'll be this kind of yellow color in an acid. So you can see how that's yellowish. Get that out of the way. And then I have my base here. I don't know if this base is strong enough, but it should change to a blue color in this base. And you can see, I had a couple drops there, it does change to a blue. So my acid is yellow, not a super strong yellow, but yellow, and my base turns blue. And of course it started off as this kind of brownish color. So that's one acid-base indicator that we can use. I'll get those out of the way. Let's see if we can't make something happen with our phenolphthalein here. So grab a couple empty beakers. All right, so phenolphthalein is a clear liquid. I don't know if you can see it in the bottom there of that. It's completely clear. So what I'm going to do is I'm going to attempt to put a couple drops in, because that's all you need, but it doesn't have a dropper on it. Oh, that's a lot. And that's good. All right, so according to my chart, phenolphthalein, which is this clear liquid, it should be completely clear in an acid. So I'll put some acid in here, and you can see it's kind of clear. It goes a little cloudy in the acid, but it's still clear. I'm going to add some base here, and you can see how it goes this really pink color in that base. So that's an indicator that's telling me that I have a base here. And again, it's kind of clear, cloudy in the acid. Now, what would happen if I mix an acid and a base together? You guys have done some reactions with acids and bases. What happens when you mix these two things together? What should my products be if I mix an acid and a base together? Anybody remember? I should end up with a couple things. All of my acid-base reactions always produce a salt and water, so it should be neutral. So yeah, Abby, you're right. If I mixed an acid and a base, I should end up with something that's neutral. So what happens to phenolphthalein if I have a neutral substance? What will happen then? Well, the phenolphthalein should change color back to a clear. So what I'm going to do is I'm just going to lose this stuff off to the side here. This had my acid in it, and this had my base in it. So what I'm going to do is I'm going to add a little bit of acid to my base with the phenolphthalein in here. And you can see it kind of disappears a little bit. See, it's kind of mixing, and if I give it a little swirl, it disappears. So what I've done is I've neutralized my base with my acid, and it goes back to clear. All right, what happens if I add a little bit of base now? So what if I shift that back to having this as being more basic now, whatever I have in here? You can see it stays clear, stays clear. It's a pretty weak base, but let's see if we can get it to go without filling up this whole thing. Starting a little bit. Just mix this up. It didn't mix very well. All right, this should go now. So you can see it start to go pink a little bit. In the middle. Of course, I ran out. But I have more on standby. Fortunately, I might run out of volume here. All right, so this is really cloudy just because I couldn't get it to mix very well. But you can see how it goes back to that kind of pinky color when I add my base. So now that the concentration of base is greater, now I can do that. And I could just keep doing the same thing where I add my acid back in here, and you can see the color will disappear as it gets neutralized. And once the indicator's there, it'll just keep telling you if you have an acid or a base. So if I add more base, it's going to go back to the pink color, and then I can add more acid and neutralize the base that I added, and it'll go back to that clear. I've run out of acid. Give this a little swish, it'll probably disappear once they mix a little bit better. So there you go. Once an indicator's there, it doesn't disappear. It's there. It doesn't actually, it's not taking part in the reaction. It's just kind of there hanging out in the background. So when we talk about indicators, they're not actually, taking part in the reaction. So if I had an acid and a base, I mix them together. Even though the indicator, that phenolphthalein's in there, it's not part of the reaction. It's just kind of saying, oh, hey, there's some base here. Now I'm going to turn pink. And then you put some acid in. Oh, the base got neutralized. I turned it into some salt and water. There's no base left. I'm going back to clear because that's how I exist when I don't have any base present. So that's how indicators work. And you can do the same thing with the bromethymol blue, or any of these indicators will do that same sort of thing. If you notice some of the indicators that you guys need to know, they're all on the chart. So you don't have to memorize these things, but something like indigo carmine, which is at the very bottom here, you can see it stays blue, 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 and then at the very end, at a very, very basic or very alkaline 13, it starts to change into yellow. So what you can do is, if I said something like, oh, I give you a substance and I added some phenolphthalein and it turned pink, but I added indigo carmine and it was blue, you can see that kind of has a small little area in here. So you know that the pH of the substance is going to be between about 10 and 12, because that's the only place where phenolphthalein can be pink and indigo carmine can be blue. So you'll end up seeing questions like that. So-and-so turned methyl orange red, and it turned bromethymol blue yellow. what is the approximate pH. So you look and say, okay, well, methyl orange is red up in this section, and then bromothymol blue is yellow in here. So I know it's going to be a pH between about 3 and 0. So that's how you're going to use this chart. All right. I think I might just take a quick break. What we'll do is we'll take like a 5-minute break so you guys can get up and move a bit. You've been sitting for a long time. And then we'll come back and we'll finish off acids and bases and salts. And it really won't be that long, maybe like another 20 to 30 minutes. So if we can just put up 5 minutes, and then I'll see you guys back, and make sure you get up, move around, grab a snack, grab a drink. We'll finish off the notes, and then we'll call it a day there. Thanks, guys. Hi guys, welcome back. If you can give me a green check to make sure everything's going okay and we have connectivity, and we'll just continue on with these notes. Shouldn't be too long, and then we'll call her a day from there. So we've talked a little bit about acids and bases. We've looked at kind of how some indicators work. So you guys make sure you're referring to that page in your data booklet. And when you guys go to write your provincial exam, you sit down. The data booklet that you guys get will be printed in color for you, and it'll be kind of in the middle of your exam. So you're gonna have a paper exam. You just tear that data booklet right out of the middle, and then you can do the test. So the data book will be in color. So if you've got it printed off at home and it's black and white and you're doing your best to answer the questions, that's fine. Remember that even though it's printed in color, in the data booklet, on the edges, it tells you the color it should be. So if you don't have it printed in color, if it's in black and white, not the end of the world. You can see where the color transition is, and it actually will say yellow on one side and blue on the other. So yeah, it's just kind of nice if you have it in color, but it's not the end of the world. There's very few questions that there's no questions you won't be able to answer if your data booklet's in black and white. You just have to read what's going on. So yeah, don't worry about that. So acids, we've talked about already. We've been able to identify them as being something that starts with the letter H. So if you have a compound that has an H, then you have yourself an acid. Now there's a couple exceptions to this rule, and we'll look at them here in a minute. So acids behave like acids only when dissolved in water. Most of the acids we deal with in science will be aqueous, same with bases. And chemical formula for acid usually starts with an H. And if you have an acid with carbon in it, we usually write the C first. So that's the only exception. So you kind of have to just know that CH3COOH is acetic acid. And it turns out that the acid that I used in my experiment here was acetic acid. And you guys have used acetic acid before, and you're thinking, Mr. Borden, you've lost it. I'm going to grab my acetic acid here. So acetic acid is vinegar. So vinegar, if you taste vinegar, it's kind of sour tasting because it's acidic. So if you look on your vinegar container, right at the top here, obviously you won't be able to read this, but it says contains 5% acetic acid. So that means of this big 4-liter jug of acid, 5% of it, or just a little bit, is acid, and then the rest is just water. So we make it very dilute so it's not going to cause serious damage. But acetic acid is an acid, and it's vinegar, and you guys use it in your everyday lives. There's lots of examples of kind of really common acids and bases that you guys will have in your houses. Ava, just reading your question here, is your provincial exam going to be on paper? Yeah. I know when we did the math one, we ran into some network issues, and I said, do we have to do it on a computer? And then they're like, well, no, it's a little bit easier if we do, but we don't have to. And I'm like, well, I think I would really like it if it was a paper exam. So that way you get the data booklet, everything's there in front of you, you got your bubble sheet. So we're gonna do it on paper. And that was my decision. So if you would prefer computer, then you can yell at me, I'll take the fault for that. But I think the paper exam's easier for science with the data booklet and everything else, because you're always using your data booklet and flipping through it. So yeah, it'll be at Hollywood Road. Not the same room we were in, but it'll be just down the hall a little further, a nice quiet room at the end of the hall. And yeah, I don't want there to be any network issues or things like that. You guys don't need to rely on the technology of a computer, batteries dying. It just seemed like it would remove a lot of kind of uncertainty from everything. So yeah, definitely a paper copy. All right, so hydrochloric acid is stomach acid, HCl. It's a very strong acid, your hydrochloric acid in your stomach. So you're talking about a pH about 1. Nitric acid, acetic acid, all of these things are acids, and they all have that hydrogen in there. The only exception is the acetic acid because it contains carbon and it's an organic molecule. You end up with the C, or I shouldn't say it's organic, but it has the C first. So CH3, we haven't talked about organics or not yet, but we will soon. So that CH3, COOH is kind of the only exception. And it kind of looks like a base if you really look at it, because it has that OH at the end. So acetic acid is kind of one of these really tricky ones. And in your data booklet, on page 5, I don't think I have trying to think of where I have this. Anyways, next to the common ion sheet, on page 5 in the top corner here, you have some common acids. So hydrochloric acid, HCl is there, sulfuric acid, H2SO4 is there, nitric acid, HNO3, and acetic acid, CH3COOH, is there as well. And you should just know where it is, and it will come in handy when you guys write your exam. You end up with some common acids that are indicated there. Kind of handy to have, or handy to know where that is. So those are acids. This is where we go from being kind of process-oriented, kind of going back to memorization. So you should be able to name acids. Now, there'll probably be one question that you'll encounter on your exam that kind of looks like this. You'll probably see a few in the unit test. But when we name acids, it depends on what the ending of our compound is. So if you have an acid just like HF or HCl, normally that would be hydrogen and fluoride is what we would call it if it was just a regular ionic compound, hydrogen fluoride. But because it starts with an H, it's an acid. So we don't call it hydrogen fluoride. We want to recognize it as being an acid. So what we do is we put the word hydro in front of it, and then fluoride changes to fluoric and acid. So anytime you have an acid that is just an H and just a nonmetal, HF, HCl, HI, that's going to be hydrofluoric acid, hydrochloric acid, hydroiodic acid. And one really easy way to remember that is on your common, on page 5 of your data booklet, HCl is there, hydrochloric acid's there. So if you forget the naming rules, there's an example of it right on your data booklet. So you don't really need to remember it, you just need to remember to look here and say, oh yeah, if it's an H and a Cl, hydrochloride changes to chloric acid. So that's one way. The next one is if you have an acid with something that ends in ate. So we have hydrogen, HCO3 is hydrogen carbonate. So we don't call it hydrogen carbonate because it's an acid. We want to give it its acid name. So instead of the ate, we change the ate to ic. So this will be carbonic acid. We don't use the hydrogen anymore. If we have HCO3, we just lose it. And we say, okay, it was carbonate. Now it starts with a H, so we're going to call it carbonic acid. And all of the ates on your common ion sheet change to ics. So you could have, let's see if I can find a couple ates. So like chrome 8 would be chromic acid. And if you had chlorate, it'd be chloric acid. If you have, there's another one, perchlorate will be perchloric acid. Permanganate would be permanganic acid. I don't know if that actually is an acid, but there you go. And again, you have an example of that in your common acid sheet. So the second one down is sulfuric acid. So if you can recognize that SO4 is sulfate, you'd be like, oh yeah, 8 changes to ic. So yeah, the compounds you were naming before were acids if you had something that started with hydrogen. Now we're just learning how to name them as acids. So generally speaking, we didn't use hydrogen very often as a metal to form a compound. We tried to avoid that just because we knew we'd talk about acids later. So some of them very well could have been acids, but You just named it how its kind of or its chemical name. Just like dihydrogen monoxide, that's water. We call it water. We don't call it dihydrogen monoxide. So same with acids. Acids have common names. Sulfuric acid. Let's look at the next one here. The last one that we can run into is our ites. So hydrogen and anything with like sulfite, we change the ite to ous. So sulfite gets changed to sulfurous acid. Sulfuric acid, what were you doing with sulfuric acid? Sulfuric acid is usually a compound that's in batteries. We put sulfuric acid in batteries. I think nitric acid sometimes in batteries as well. So anytime we have an ous, or an ite, so we change it to ous. And none of the common acids end in ous. So you don't have any examples of that on here to refer to. But if I were to look on my common ion sheet, I find something that's called ite. So hypochlorite would be hypochlorous acid. Nitrite would be nitrous acid. Phosphite would be phosphorus acid. Sulfite, sulfurous acid. And there you go. So those are the three. Those are the three sort of naming principles that you'll run into. Not a huge idea. It doesn't come up a lot, but it is one that does come up. So it's important to know the three naming rules. And the good news is 2 of the naming rules are on your data booklets. You don't even need to memorize them. But the third one, the ites changing to ous, that one does show up. And it's not in your data booklet. H2SO4 was in a song. That's quite a song. I can't imagine that would be a popular culture type song. So that's acids. There you go. Bases are easy compared to acids. They don't have any fancy names. They are usually pretty straightforward. So bases end in OH. You guys know that. There's no exceptions to this rule. It'll never not end in OH. So there you go. Bases are really slippery when you touch them. So things like soap. Why is soap really slippery? Well, it's made of base. Not a very strong base, but it has a base in it. And bases are good cleaners, so we use them for cleaning, like baking soda, ammonia, bleach, soap. These are all bases, and they are all cleaners. So here's some examples of really common bases. We have something like NaOH, so that's sodium hydroxide, MgOH, magnesium hydroxide, CaOH, calcium hydroxide, and the base I used for our demonstration here was calcium hydroxide, so that's the only one I could find. NH4 is ammonium hydroxide. And yeah, so bases are super easy to name because they just have their regular ionic name. There's no special rules for bases. There's no ouses and ites and ics and anything like that. It's just sodium hydroxide, potassium hydroxide, whatever the OH has in front of it, and you just name the hydroxide next. So bases are easy. Always end in OH, that's the important part. Usually dissolved in water. There you go. Now, this kind of idea is maybe a bit confusing, but I think you guys can get it. When we mix acids and bases, we usually mix them with water. And when an acid or a base goes into water, it doesn't stay stuck together like H2SO4, sulfuric acid. It doesn't stay stuck together. What happens is the SO4 group kind of floats off, and then the H group floats off. And that's because water is slightly polar, so has a bit of a charge to it. And sometimes when we dissolve compounds in water, they break apart, they dissociate. So when we put an acid in water, it doesn't stay together as an acid, it kind of dissolves into the H and the Cl or whatever's there. And bases do the same thing. So if I had calcium hydroxide, the calcium is going to kind of move off and the hydroxide is going to separate and they're going to float around by themselves. So one thing that's kind of a science convention that you'll see a lot of if you move on in science is these square brackets. If I put a square bracket around something, that means concentration of that thing. So it's a way of telling you how concentrated it is. Now, when we looked at reaction rates, we talked about the more concentrated, the faster the reaction is going to happen. And we use the example of drink mix. If I put lots and lots and lots of drink mix into a pitcher and mix it up, it's really sweet. It's a really high concentration. If I have just a few sprinkles of drink mix, low concentration. So if I had square brackets, that just means the concentration. So it means it's dissolved in water and how much concentration you have. So something can't have a high H or a high amount of hydrogen and a high amount of OH at the same time, because just like when I had the phenolphthalein next to me and I added that acid, the base disappeared. Remember, you have a neutralization happening with the H and the OH form water. So if you have a bunch of base getting added, a bunch of base, all the acid's gonna kind of combine to form water until you run out of acid, and then you get these OH molecules kind of floating around, and then the phenolphthalein turns pink because there's a bunch of OH floating around in there. If I add some more acid, I'm adding a bunch more H's. The H's and the OH kind of bond together until I don't have any more OH left, and then the solution's no longer pink because all the OH is gone, and then I have extra hydrogen in there now. So that's what's going on there. There's a little chart at the top of your acids and bases chart. This is actually up there, and it shows you the more acidity you have, the higher the concentration of hydrogen. And then in the very middle, you have a perfect balance between hydrogen and oxygen, or hydrogen and hydroxide, and you end up with just pure water in the middle. And then if I add a little more base, now all of a sudden I have more OH being produced, more OH molecules in there, and it's slightly basic. What does pH stand for? I forget. I think it's production of hydrogen or something like that. The P is for production, H is for hydrogen. Don't quote me on that though, it's just off the top of my head. I'm sure if you searched it on the internet, you could find it really quickly. Quicker than my brain. So here's just a chart, just a summary of kind of acids and bases in general. Now it says taste and touch, of course, but we're not going to talk about tasting chemicals or touching chemicals because it could burn your skin. You don't want to taste it and make you very sick. But if you were to taste an acid, it'd be very sour, and bases taste kind of like bitter. And then touch. Acids are going to burn your skin. Sulfuric acids and batteries. Potential hydrogen. Thank you, Taylor, for finding that for me. Production hydrogen, I was off by a little bit. Bases feel slippery, so they'll also burn your skin. So both acids and bases can burn your skin if they are concentrated enough. Indicators. So we talked about our indicators chart. Acid's going to turn blue litmus blue. Acid's going to turn blue litmus red, and red litmus will stay red. And indicators and bases are going to end up being blue, and then phenolphthalein is a common one, so it's going to be pink in a base. So we looked at that. The one problem you can run into with litmus paper is sometimes if you're testing something to be an acid or a base, if you put it in an acid and it stays clear, you don't know what it is, it stays red maybe, and then that thing could be neutral. So there's a chance that what you're testing isn't acidic or basic, it's just maybe water or something else that doesn't have an acid or a base in it. So you can't determine if something is acidic or basic unless it changes the litmus paper color. So if I put red litmus in something and it comes out red, I can't say, oh, that's a base. I don't know that. It could be neutral. It could be a base. I don't know. So there you go. Indicators are only so good. If things are neutral, you can run into problems. Both acids and bases will conduct electricity because of the charges that they have. pH of less than 7 for an acid, greater than 7 for a base, and acids are produce the H plus ion, and bases produce that OH when dissolved in water. And that's easy to remember because you guys know that acids always start with H and bases always end with OH. So that's a nice little summary of all of that. that's it for acids and bases, and I think that's a pretty good spot to stop for today. Does anybody have any questions about the course or acids and bases or learning guides or anything like that? I was hoping your Unit 4 learning guide would have been submitted yesterday. I'm going to submit my marks for report cards by the end of the day today, so if you check your mark and something's missing or I haven't marked something, let me know. I can still change it. There's still time. But if not, your mark, whatever you have right now, should be your Term 3 mark. I'm going to mark the Unit 4 learning guides probably tomorrow or maybe Monday. And then you guys will continue on through the course. So Unit 6, we finished. Let's submit that by Monday. Unit 5, which we're doing, or sorry, Unit 6. Yeah, Unit 6 Monday. We're in the middle of Unit 5, so that'll be middle or end of next week. So we do need to write the Unit 6 test. Yeah, I did say, thank you, Anna. So Unit 6 test needs to be written. So let's do that by, if you get your learning guide in on Monday, you can write the test by Tuesday, hopefully. So that'll work for Unit 6. Unit 5, we have one more class Unit 5, and then we're done. So we'll probably be done Unit 5 next week sometime. And that's kind of where we're at. So we'll have a Unit 6 and a Unit 5 test next week. They're very, very short units. There's not a lot of information there, so don't be like, oh no, but it'll be done really quick. There's no test for Unit 4. We had the midterm with all of the compounds on it. And then some of the stuff at the end of Unit 4 was balancing, which we end up doing in Unit 6 anyways, so it kind of really worked out well. After Unit 5, we're going to jump to Unit 7, which is radioactivity. And yeah, there you go. If you do the Unit 6 learning guide today, I can mark it, but I'm not going to enter your mark online because that's going to mess up my grades for Term 3. So I need to leave myself a little bit of a gap before I start marking things again. Because as soon as I put new marks in, your overall grade's going to change, and that becomes a problem with submitting marks for report cards and whatnot. So I want to get your first sort of 5 units straightened out midterm, and then I'll maybe move on after, maybe tomorrow or the next day. So that's it. For me, hopefully I answered all your questions. If not, send me a message and we can figure it out. And I hope you guys have a great weekend. Hopefully we see you golfing tomorrow. Mrs. Wood, who's been to the first 2, said that some of you guys are like getting really good at golf, showing some really good improvement. Really easy sport to play. Frustrating, but easy. So you should come out. It's supposed to be nice. And if not, have a great weekend and we'll see you next week. Thanks.